Traditional assembly lines operate under the historical assumption that stockpiled inventory is a valuable asset. This just-in-case methodology maintains a massive cushion of parts to ensure that the next workstation always has materials ready to process. Modern financial planning views excess inventory as a financial liability. Every box sitting idle on a factory floor represents liquid capital that is tied up and at risk of obsolescence or physical obsolescence. Traditional manufacturing relies on a push model. In this setup, central management generates a forecast of anticipated market demand, and that forecast dictates how many parts are manufactured and pushed down the line, regardless of whether the next station is ready for them. Modern operations favor demand-driven pull models. Here, output is strictly limited to the immediate needs of the subsequent operation, with parts arriving only when they are required. To understand modern cost management, we must map a mechanical shift from push to pull systems across the factory floor. Transitioning from massive inventory buffers to zero-waste production alters a company's unit economics, its enterprise data architecture, and how it measures its own capacity. Supply chain management serves as the primary mechanical lever, controlling the accuracy and health of the entire corporate balance sheet. The traditional push system is managed through Materials Requirements Planning, or MRP. MRP is a computerized system for moving materials through a production process according to a predetermined schedule. The logic driving MRP begins with a master production schedule, a rigid forecast of final product demand. Once that schedule is programmed, the system calculates the raw materials needed and pushes required orders backward through the supply chain. This table displays the bill of materials for a main product labeled AA115. To hit a baseline requirement of 40 finished units, the system catalogs the exact quantity of necessary subunits, specifically the CM12 and PR75 components, while tracking the inventory quantities currently on hand. Looking at the to be built calculation row, the schedule requires 200 total units of the PR75 component. The system mathematically subtracts the 35 units already in the warehouse, dictating that exactly 165 units must be built. This cascading timeline translates those raw component calculations into a rigid schedule based on lead times. Lead time is the total amount of time between when a process starts and when it is completed. To ensure the final product is ready by the week 6 due date, the order for the PR75 subunits must be placed exactly 3 weeks prior. This rigid mathematical pacing creates an operational vulnerability. To prevent stockouts and missed schedules, an MRP system requires maintaining high inventory buffer levels as a safety net. These deep buffers mask serious production problems. When a machine produces a batch of defective parts, the assembly line does not stop because workers simply reach into the massive pile of buffer inventory to keep the line moving. The traditional push system successfully guarantees scheduling security, but it buys that security by accepting hidden operational waste and normalized defects. This illustrates the physical dismantling of the traditional linear assembly line. Isolated single-task workstations are broken apart and rearranged into continuous semicircular manufacturing cells. This layout is the foundation of just-in-time, or JIT, manufacturing. JIT is a pull system where output is strictly dictated by current active customer demand, rather than being pushed through by anticipated schedules. DeShift involves the complete elimination of centralized receiving areas and massive storage warehouses to remove non-value-added handling. Components and raw materials arrive at the cell exactly when they are needed. Instead of moving between specialized departments, each semicircular cell functions as a self-contained miniature manufacturing plant dedicated to producing a given product or product family. Operating a self-contained cell requires multi-skilled labor. Workers must be able to operate all machines and simultaneously perform support tasks, such as machine setups, preventive maintenance, and quality inspections. Multi-skilled teams require empowerment. Under a JIT system, workers have the authority to completely stop production to correct a sudden problem, rather than pushing a defect down the line. This exposes the factory to the constant, looming threat of a complete stockout because the company no longer maintains inventory buffers. That exact risk is what enforces rigid quality control. Because there are no extra parts, a single defect will immediately halt the entire production line, forcing the team to solve the problem instantly. JIT forces higher quality not through better inspections, but by removing the safety net of excess inventory. The focus shifts entirely towards zero-defect prevention. A lean factory operating with zero buffers requires instantaneous data communication across the company to function. To achieve this, localized MRP software evolved into Traditional Enterprise Resource Planning, or ERP. ERP is a system that integrates enterprise-wide information systems across an organization into a single database linked to all applications. As shown in this diagram, traditional ERP acts as a unified back-office database. It connects the factory floor's materials schedule directly to internal modules for human resources, financials, and production. The next evolution is ERP2. This generation adds front-office functions, providing the capability for instant interaction with external parties like customers and suppliers. Supply chain management applications facilitate a bidirectional data exchange. Supply chain management focuses on the relationships extending from raw material suppliers through to the final customer, allowing suppliers to monitor customer inventory for real-time replenishment. Simultaneously, customer relationship management applications feed external sales forecasts directly back into the manufacturing cells. CRM is a technology managing all organizational relationships and interactions with current and potential customers. Modern manufacturing requires the entire network, from raw material vendors to the CFO, to function as a single, fully integrated reactive organism. The ultimate financial consequence of these systems comes down to overhead. Accountants must allocate the fixed facility costs to the final products regardless of the manufacturing model used. This graphic displays the core accounting formula for determining indirect product costs. The overhead application rate is calculated by taking the estimated total overhead and dividing it by an estimated allocation base. Theoretical capacity assumes optimal output with zero downtime and zero waste. Applying these variables, dividing $10 million in overhead by an unrealistic 100,000 unit capacity yields an artificially low rate of $100 per unit. Budgeting based on theoretical capacity is a planning fallacy. No physical factory operates without routine maintenance, machine breakdowns, or setup delays. Practical capacity is used for accurate results, factoring in expected maintenance and downtime. Updating the denominator to a realistic 90,000 units recalculates the application rate, raising the cost per unit to $111.11. Choosing theoretical over practical capacity inflicts immediate financial damage. Artificially diluting the application rate leads directly to underpriced products that bleed profit margin on every unit sold. This creates a severe year-end balance sheet consequence. Because actual production will inevitably fall short of a theoretical maximum, using that metric guarantees massive underapplied overhead variances. These variances must all eventually be reconciled. When they are closed out, they correct the cost of goods sold, tanking the company's reported operating income. A factory's operational structure and capacity measurement serve as the absolute bedrock of accurate product pricing and corporate survival.